Picture this: an endless black sea of nothingness, stretching across the cosmos for millions of years. No stars, no galaxies, just darkness swallowing everything in its path. But then something extraordinary happened. The universe flickered awake, as if someone flipped a cosmic switch, scattering light into the void for the very first time. What if I told you that this moment, the Cosmic Reionization Era, is one of the greatest unsolved mysteries in all of space? A time when the universe essentially hit the reset button, tearing itself out of the dark ages and birthing the glittering cosmos we know today. For centuries, scientists have pieced together the story of the Big Bang and the formation of galaxies, but this period when the universe was reborn in light remains shrouded in secrets. How did it happen? What forces were at play? And why did it take hundreds of millions of years for the cosmos to finally wake up? These aren't just idle questions, they're the keys to understanding the very fabric of our existence. Because without this cosmic reboot, the universe as we know it, with its swirling galaxies, blazing stars, and even us wouldn't exist. That's why today we're diving deep into 25 of the most baffling, mind-bending mysteries of the Cosmic Reionization Era. From the elusive first stars that ignited the darkness to the colossal bubbles of ionized gas that rewrote the rules of space itself, we'll uncover how this hidden chapter shaped everything around us. So buckle up, because we're about to journey back in time to an era when the universe was nothing like it is today, and yet in so many ways everything was just beginning. If you were to point a telescope back to the very dawn of the cosmos, you'd see a universe drowning in darkness, a place where atoms were still whole, floating undisturbed in an endless void. Then suddenly something shattered the silence. The very first light tore through the blackness, stripping electrons from atoms in a violent, irreversible transformation. But here's the puzzle: what exactly flipped the switch? The leading suspect, the first generation of stars, colossal, short-lived giants known as population 3 stars. Unlike anything in our modern universe, these behemoths burned hot and fast, packing hundreds of times the mass of our Sun into a single, searing furnace. When they died in spectacular supernova, they might have blasted the surrounding gas with enough ultraviolet radiation to rip atoms apart, sparking reionization like a chain reaction. But not everyone's convinced. Some theorists argue supermassive black holes could have played the villain. Imagine quasars, the brightest objects in the universe, powered by voracious black holes devouring matter at terrifying speeds. Their sheer energy might have punched holes in the cosmic fog, carving out bubbles of ionized gas long before stars had a chance to take center stage. And then there's the wild card: dark matter. What if an exotic, undiscovered particle decayed in those early epochs, releasing energy that pried electrons loose? It's a fringe idea, but if proven true, it would rewrite physics itself. The stakes couldn't be higher. Pinpointing the trigger isn't just about solving a cosmic whodunit. It's about understanding how light sculpted the universe. Because without reionization, those first galaxies might never have formed, leaving the cosmos forever lost in the dark. The deeper astronomers dig into the Cosmic Reionization Era, the more one question keeps splitting the scientific community right down the middle: when did this cosmic dawn actually happen? You'd think pinning down a timeline would be straightforward, but the universe loves a good plot twist. Depending on which cosmic clue you follow, ancient quasars, ghostly afterglows from the Big Bang, or distant galaxy surveys, you'll get wildly different answers, ranging from a mere 150 million years after the Big Bang to a staggering 1 billion years later. That's a discrepancy wider than the Milky Way itself. Start with quasars, the brilliant lighthouses of the early universe. These monstrous black holes, feeding on gas and spewing radiation, leave behind fingerprints in the form of absorption lines in their light. Some observations suggest their surroundings were already ionized as early as 800 million years post-Big Bang. But here's the catch: Other quasars from the same era show patches of lingering neutral hydrogen like cosmic shadows refusing to fade. So was reionization wrapping up by then, or was it still flickering in fits and starts? Then there's the cosmic microwave background, the oldest light in existence. Satellite missions like Planck have scoured this faint glow for hints, detecting subtle distortions caused by free electrons from reionization. Their data points to a much earlier timeline, suggesting the process was halfway done by just 450 million years. But wait, galaxy surveys throw yet another wrench into the mix. Peering at some of the first galaxies ever formed, telescopes like Hubble and James Webb spot pockets of ionized gas as late as 1 billion years after the Big Bang. If reionization was truly over by then, why do these galaxies act like they're still cleaning up the mess? The truth might lie somewhere in the chaos. Maybe reionization wasn't a single, uniform event but a patchwork quilt of ionization, some regions blazing to life early, others stubbornly clinging to darkness. Picture a forest fire where some trees ignite instantly while others smolder for ages. Or perhaps our tools are simply too limited, like trying to reconstruct a symphony by listening to disjointed notes. Until we can observe this era in higher resolution, the debate will rage on. One thing's certain, solving this timeline tug-of-war isn't just about dates, it's about unraveling how the universe transitioned from simplicity to complexity, from darkness to light. And that's a story worth waiting for. Here's a cosmic head-scratcher for you. What if the entire reionization story was missing its most crucial character? Scientists call it the photon underproduction crisis, and it's exactly what it sounds like. When astronomers tally up all the ultraviolet light needed to rip electrons from atoms during reionization, they come up horrifyingly short. The numbers just don't add up. Even if every known star and quasar in the early universe worked overtime, they'd still fall billions of photons shy of the energy required to pull off this cosmic feat. So where's the missing light? Either we've overlooked something monumental, or our understanding of this era is fundamentally flawed. One leading theory points to the unsung heroes of the cosmos, dim dwarf galaxies. These tiny, faint galaxies are notoriously hard to spot across billions of light years, especially with telescopes limited by today's technology. But what if they were lurking in the shadows all along, pumping out UV radiation in vast quantities? Early data from the James Webb Space Telescope hints at a population of such galaxies previously invisible to us. If confirmed, these overlooked powerhouses could flood the early universe with enough photons to tip the scales. Then there's the possibility of exotic, high-energy phenomena we've yet to discover. Picture this: cosmic particle accelerators powered by colliding neutron stars or supercharged magnetic fields, unleashing torrents of ionizing radiation. Some models even suggest that dark matter, if it interacts in unexpected ways, could have decayed into bursts of UV light, stitching together the gaps in our photon budget. But the most unsettling option: our models might be dead wrong. Maybe reionization didn't require as many photons as we think, thanks to some overlooked quirk in how gas was distributed back then. Or perhaps the process was far more efficient, with photons bouncing between atoms like cosmic pinballs, ionizing far more than their energy should allow. Either way, this crisis forces us to confront an uncomfortable truth. We might be staring at the universe's baby photos with all the wrong assumptions. And until we solve it, the story of cosmic dawn remains frustratingly incomplete. Imagine the universe during reionization as a pot of water slowly coming to a boil. The question dividing astronomers: did it heat up evenly like a simmering broth, or did bubbles of ionized gas burst forth sporadically, like pockets of steam erupting across the surface? This isn't just academic nitpicking. The answer could redefine our entire understanding of how structure emerged in the cosmos. On one side of the debate, you've got the smooth camp scientists who argue reionization was a gradual, uniform process. Picture fog lifting steadily under morning sunlight, with UV radiation from early stars and galaxies permeating space evenly. Proponents point to the cosmic microwave background's subtle polarization patterns, which suggest a relatively even distribution of free electrons. If they're right, it implies the first light sources were scattered densely enough to avoid leaving shadowy gaps in the universe's rewiring. But the Clumpy theorists paint a far wilder picture. They envision a cosmic Swiss cheese where ionized bubbles erupted unpredictably around the fiercest radiation sources, quasars, and massive star clusters, while vast regions of hydrogen stubbornly clung to neutrality. Evidence: distant quasars sometimes show alternating bands of ionized and neutral gas along their sightlines, like tree rings recording eras of cosmic turbulence. And let's not forget those stubborn patches of hydrogen that lingered far longer than smooth models predict, like unpopped kernels in microwave popcorn. The Game Changer, a revolutionary tool eavesdropping on the universe's oldest whispers, 21-centimeter radio telescopes. These instruments detect the faint hum of hydrogen atoms from the early cosmos, a wavelength stretched over billions of years into the radio band. Projects like the Square Kilometre Array and the Hydrogen Epoch of Reionization Array are creating 3D maps of this ancient gas. Early data already hints at a bumpy reionization landscape, with some regions ionizing shockingly fast while others lagged behind. But the real breakthrough will come when these telescopes peer deeper, revealing whether those bubbles overlapped like soap suds or left sprawling deserts of untouched hydrogen. What's at stake goes far beyond bragging rights in astrophysics circles. If reionization was clumpy, it means the first galaxies didn't just light up the universe, they reshaped it in uneven bursts, forging cosmic inequities that might have seeded the vast voids and superclusters we see today. A smooth process, by contrast, would suggest a more orderly, predictable evolution. Either way, the answer hides in those faint radio signals waiting to rewrite the story of how our universe grew up. What if the invisible architecture of the cosmos played puppet master during reionization? Dark matter, the mysterious, gravity-wielding substance that outweighs normal matter 5-to-1, might have orchestrated the entire show from the shadows. While it doesn't emit or absorb light, its gravitational pull sculpted the earliest structures in the universe, creating dense webs where galaxies could ignite and flood space with ionizing radiation. But here's the twist: dark matter's influence might go far beyond just setting the stage. New simulations suggest it could have directly shaped how and where reionization unfolded, leaving fingerprints we're only now learning to decode. Take the cosmic scaffolding theory. Supercomputer models revealed dark matter's tendrils formed vast, interconnected filaments long before stars flickered to life. These invisible highways channeled gas into dense knots, birthing the first galaxies in clustered pockets rather than evenly across space. The result: reionization didn't spread like a uniform tide but erupted in fiery waves along these hidden corridors, leaving behind a patchwork of ionized bubbles. Some simulations even showed dark matter's gravitational quirks could have delayed reionization in certain regions by slowing gas collapse, creating cosmic deserts where neutrality stubbornly persisted. Then there's the self-interacting dark matter hypothesis, a game changer. If dark matter particles occasionally collide like billiard balls ricocheting in space, they'd smear out the densest clumps, softening galactic cores. This subtle tweak could explain why some early galaxies produced torrents of UV radiation while others barely contributed. Intriguingly, observations of faint, diffuse galaxies from the James Webb Space Telescope align eerily well with these predictions, hinting that dark matter's stickiness might have fine-tuned reionization's pace. But the most tantalizing clue comes from the Lyman alpha forest, a bizarre pattern of absorption lines in quasar light. These lines trace the distribution of neutral hydrogen during reionization, and their spacing matches simulations where dark matter's gravitational waves compressed gas into precise, large-scale patterns. It's as if the universe's invisible skeleton left shadows in the light. Of course, not all models agree. Some theorists argue dark matter's role was indirect, merely corralling gas to birth galaxies, while stellar radiation did the heavy lifting. Others propose wildcard scenarios where decaying dark matter particles themselves emitted ionizing photons like stealthy cosmic arsonists. The truth likely lies somewhere in between. One thing's certain, unlocking dark matter's connection to reionization isn't just about filling gaps in our cosmic timeline. It's a chance to glimpse the hidden hand that shaped everything we see and everything we can't. They were the universe's first pioneers, monstrous ephemeral giants that burned brighter and died younger than anything we've ever seen. Population 3 stars, the hypothetical first generation of celestial bodies, were unlike anything in today's cosmos. Picture a star so massive it could dwarf 1,000 suns, glowing with a blue-white ferocity that made modern stars look like dim candles. These titans were forged from pristine hydrogen and helium, untouched by the heavier elements that clutter later stellar generations. And when they exploded, they didn't just die, they transformed the universe, seeding it with the first heavy elements and flooding space with the ultraviolet radiation that may have kicked off reionization. So why have we never spotted one? The answer lies in their brutal, fleeting existence. These stars lived fast, some lasting only a few million years before self-destructing in cataclysmic supernova. By cosmic standards, that's barely a blink. Compounding the challenge, they formed in an era so ancient that their light has been stretched beyond recognition by the expansion of the universe, slipping into the infrared spectrum where only the most advanced telescopes can glimpse them. Even then, their individual signatures blur into the haze of their host galaxies, like trying to pick out a single firefly in a stadium of floodlights. But hope isn't lost. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is hunting for their ghosts. Instead of chasing the stars themselves, scientists are scouring distant galaxies for chemical fingerprints, trace amounts of elements like carbon or oxygen that could only have been forged in the cores of population 3 stars. Some early Webb observations have already spotted galaxies with shockingly low metal content, hinting at populations of these ancient beasts lurking within. Other teams are searching for the unique light patterns these stars would have emitted, like a cosmic barcode etched in ultraviolet fury. The implications of finding them go far beyond ticking a box in astrophysics. If population 3 stars were the primary drivers of reionization, their extreme energy output would explain how the universe's gas was ionized so quickly. But if Webb comes up empty, it could mean we've been wrong all along. That reionization was sparked by something even more exotic, like dark matter annihilation or primordial black holes. Either way, the hunt for these elusive giants isn't just about solving a cosmic cold case. It's about uncovering the very architects of light, the ones who tore the universe from darkness and set the stage for everything that followed. Quasars should have been the universe's ultimate outliers, rare, freakish monsters lurking in the cosmic backwaters. Yet the more we peer into the early universe, the more we find these supermassive black holes everywhere, flaunting their brilliance mere hundreds of millions of years after the Big Bang. That's like discovering a fully grown blue whale in a toddler's swimming pool. Their sheer prevalence throws us into a crisis. Could these voracious beasts have been the unsung architects of reionization, pumping out enough radiation to strip electrons from atoms across the cosmos? Recent observations from the James Webb Space Telescope have turned this theory from fringe to front page. Instead of the handful of quasars we expected in the universe's first billion years, Webb has spotted dozens, some shining with the brightness of trillions of suns. Even more bizarre, their host galaxies appear shockingly underdeveloped, lacking the stellar heft needed to feed such monstrosities. It's as if these black holes skipped galactic childhood entirely, ballooning to unfathomable sizes almost overnight. Conventional physics can't explain how they grew so fast unless they were born big, perhaps from the direct collapse of primordial gas clouds, or even as remnants of exotic quantum fluctuations in the infant universe. But here's the real kicker: their radiation profiles are perfect for reionization. Unlike stars, which emit most of their energy in visible light, quasars blast unfiltered ultraviolet and X-rays precisely the wavelengths needed to tear electrons from hydrogen atoms. Simulations now suggest that just one of these early quasars could have ionized every atom for tens of thousands of light-years around it. Stack dozens or hundreds across the young cosmos, and suddenly the photon budget crisis starts to make sense. Not everyone's sold, though. Critics point out that quasars were still too sparse to ionize the universe evenly. Their radiation beams were likely narrow and directional, like cosmic blowtorches, leaving vast swaths of darkness untouched. And then there's the timing problem. Some of the oldest galaxies show signs of advanced ionization before the first quasars flickered to life. So were they the main event, or just backup players in a drama already underway? The answer might lie in the shadows. Upcoming surveys hunting for fainter, more distant quasars could reveal whether these objects were truly as rare as we once thought, or if we've only seen the tip of a very ancient iceberg. Because if early quasars were even slightly more common than current models predict, they might rewrite the entire story of cosmic dawn. Imagine a universe where light didn't spread gently from countless tiny stars, but erupted in violent bursts from the maws of ravenous black holes. Now that's a plot twist worthy of the cosmos. If the universe had followed the rules of physics textbooks, the leftover hydrogen gas after reionization should have cooled into a quiet, frigid haze like steam settling after a boiling pot is removed from the heat. But the cosmos loves breaking expectations. Observations reveal this ancient hydrogen stubbornly stayed warm, defying every conventional model. This anomaly, known as the hydrogen heating puzzle, has astronomers scrambling for answers because something, somewhere, was pumping energy into the universe's leftover gas long after the lights came on. One clue lies in the Lyman alpha forest, a bizarre pattern of absorption lines seen in light from distant quasars. These lines act like cosmic thermometers, and they show hydrogen temperatures rising instead of falling as we look deeper into the past. The staggering implication: some mysterious heat source kept cooking the gas for hundreds of millions of years post-reionization. Enter the dark matter wildcard. Could this invisible substance, which outweighs normal matter 5-to-1, have played arsonist? One radical theory suggests certain types of dark matter particles, called Miller-charged particles, might have subtly interacted with hydrogen atoms. Picture this: as these ghostly particles zip through space, their weak electric nudge could have transferred energy to the gas, like a hailstorm gently warming a pond's surface. Simulations show this could explain the heating patterns we observe without disrupting other cosmic structures, but not all ideas require new physics. Another camp points to long-overlooked astrophysical engines, faint, wandering quasars or hyperactive dwarf galaxies too dim for our telescopes to spot directly. These objects flickering in the cosmic backwaters might have bathed the gas in persistent X-rays, like a slow-burning furnace maintaining the universe's temperature. Recent James Webb data hints at a population of such hidden objects, their cumulative heat potentially solving the puzzle without invoking exotic particles. The most unsettling possibility: we've misunderstood reionization entirely. If the process was far more turbulent than current models suggest, with galaxies and black holes erupting in chaotic bursts, the resulting shockwaves could have heated the gas unevenly, leaving pockets simmering for eons. It would mean the cosmos didn't transition smoothly from darkness to light, but convulsed through a fiery adolescence we're only beginning to decode. Whatever the answer, this puzzle isn't just about hydrogen's temperature. It's a window into the forces that shaped the universe's structure, forces we're still struggling to name. And until we crack it, we're left staring at the cosmic equivalent of a crime scene where the evidence is everywhere, but the culprit remains just out of sight. The cosmic web isn't just the universe's skeleton, it's the hidden conductor of reionization's grand symphony. Picture a vast, interconnected network of gas filaments, stretching billions of light years like an invisible neural network, with galaxies clustered at their intersections like glowing pearls on a string. This intricate architecture didn't just exist during reionization, it directed it, channeling radiation along its tendrils with breathtaking precision. New supercomputer simulations reveal how these cosmic highways became the universe's first light rail system, guiding ionizing radiation far beyond the reach of individual galaxies and accelerating the end of the cosmic dark ages. Consider the latest 3D visualizations from projects like Thesan and Quasar 3. They show ultraviolet radiation from early galaxies surging through filaments like electricity through a circuit, ionizing hydrogen gas at scales previously thought impossible. Dense knots of matter acted as amplifiers, focusing and scattering light into the voids, while thinner filaments carried radiation like fiber optic cables deep into the cosmic hinterlands. The result, reionization didn't spread outward in uniform spheres. It rippled, following the web's contours in jagged, lightning-bolt patterns. But here's the twist: the web didn't just passively transmit light, it filtered it. Heavy elements forged in the first supernova clung to these filaments, creating zones where certain wavelengths of radiation were absorbed while others raced ahead. This cosmic sorting system might explain why some regions ionized faster than others, even when they were equally distant from light sources. It's as if the universe had built-in traffic signals, regulating the flow of energy on a galactic scale. The implications are staggering. If the cosmic web truly steered reionization, then the universe's largest structures didn't just emerge after this era, they shaped it. Those wispy filaments, once considered mere byproducts of gravity, turn out to be active players in one of cosmology's most pivotal chapters. And that raises an even deeper question. Did the web's structure leave hidden fingerprints in today's galaxy's subtle patterns we're only now learning to read? The answer might be hiding in plain sight, woven into the very fabric of the cosmos. When we think of cosmic heavyweights, colossal galaxies brimming with billions of stars should dominate the story of reionization. But the universe loves flipping expectations upside down. Recent observations reveal a head-scratching paradox. It's actually the smallest galaxies that appear to have done the lion's share of ionizing work. These cosmic underdogs, some barely 1,000th the mass of the Milky Way, seem to have punched far above their weight, flooding the early universe with ultraviolet radiation while their larger cousins lagged behind. This discovery doesn't just tweak our models, it threatens to overturn entire theories about how galaxies shape the cosmos. Take the evidence from the James Webb Space Telescope. When astronomers calculated the ionizing output of early galaxies, they found a bizarre inverse relationship. The smaller and dimmer a galaxy was, the more efficiently it produced the ultraviolet photons needed to strip electrons from hydrogen. Some of these dwarfs were leaking up to 20 times more ionizing radiation relative to their size than their giant counterparts. It's like comparing a firefly to a floodlight, only to discover the firefly is somehow brighter. So what's their secret? Three leading theories are battling it out. First, the escape fraction, the percentage of ionizing photons that actually break free of a galaxy's gas clouds. Small galaxies have weaker gravity, meaning their gas is more loosely packed, allowing UV light to slip through cracks that larger galaxies would seal shut. Picture trying to escape a crowded stadium versus a half-empty alleyway. The latter offers far fewer obstacles. Then there's stellar demographics. tiny galaxies lack heavy elements, forcing them to form stars from pure hydrogen and helium. These pristine conditions birth massive, unstable stars that burn hotter and die younger, spewing UV radiation like cosmic flamethrowers. Meanwhile, bigger galaxies polluted by earlier supernova produce tamer, longer-lived stars great for longevity but terrible for ionization efficiency. But the wildcard theory suppressed black holes. Large galaxies almost always host supermassive black holes at their cores, whose energy output can actually quench star formation by blowing gas away. Without these central monsters, small galaxies could have sustained frenzied star-making sprees, turning them into relentless UV factories. The implications are staggering. If confirmed, it means reionization wasn't driven by the universe's brightest behemoths, but by countless faint specks of light we're only now learning to see. Astrophysicists are racing to test these ideas, but the paradox already demands a rewrite of galaxy evolution textbooks. If small galaxies were the unsung heroes of cosmic dawn, it means our entire framework for how structure emerges in the universe might be missing a crucial chapter, one where the littlest players wielded the greatest power. They called it the metal-free universe, a realm where the very concept of chemistry had yet to be invented. In those primordial epochs before the first supernova scattered heavier elements into the void, every gas cloud, every newborn star, every wisp of cosmic matter consisted of just hydrogen and helium. This elemental purity wasn't just a quirk of the early cosmos, it was the defining feature that made reionization possible in the first place. Without even a whisper of carbon, oxygen, or iron to muddy the waters, the universe operated by rules so alien they might as well belong to another reality. Consider the stars that formed in this pristine environment. Unburdened by metals, they could grow to monstrous sizes hundreds of times the mass of our Sun because heavy elements act like a cosmic coolant, helping gas clouds fragment into smaller, more stable clumps. Without them, gas collapsed into single, gargantuan behemoths that burned at temperatures dwarfing anything in today's universe. These stars didn't just emit ultraviolet light. They drowned their surroundings in it, flooding space with ionizing radiation capable of stripping electrons from hydrogen atoms in vast quantities. But here's where it gets counterintuitive. Even the tiniest contamination, a few atoms of carbon per million hydrogen atoms, could have radically altered this process. Heavy elements are greedy for electrons. Introduce even trace amounts and suddenly, those ultraviolet photons that would have ionized hydrogen get hijacked, absorbed by metals before they can do their cosmic work. It's like throwing a handful of dust into a spotlight beam. The light still exists, but its reach is dramatically shortened. This delicate balance explains one of reionization's greatest puzzles, why the process didn't sputter out prematurely. Had metals proliferated too early, they might have smothered the universe's ability to ionize itself, trapping it in a semi-neutral twilight state. Instead, the first heavy elements were likely confined near their parent stars, leaving vast stretches of intergalactic space untouched and vulnerable to ionization. The smoking gun, distant quasars whose light passes through ancient gas clouds show a striking pattern. Regions with barely detectable metal content exhibit much stronger signs of ionization than slightly richer ones. It's as if the universe had a narrow window of opportunity to reionize, one that would have slammed shut the moment metals became widespread. This metal-free era wasn't just a backdrop to reionization. It was the stagehand working the lights, the unseen force that made the cosmic dawn possible. And that raises an eerie question. Had the first stars been just slightly less efficient at dispersing their heavy elements, might we still be living in the dark ages? Picture a radio station broadcasting from the edge of time itself, a faint, static-laden transmission from an era when the universe was barely a toddler. That's the 21-centimeter signal, the holy grail of cosmic reionization research. emitted by cold hydrogen atoms drifting through the early cosmos. This whisper-thin radio hum holds the potential to map the universe's transformation from darkness to light with unprecedented precision. But here's the catch. After decades of searching with increasingly sophisticated telescopes, this signal remains stubbornly elusive, hiding in a fog of cosmic interference and technical hurdles that push our engineering limits to the brink. Why is this single wavelength so special? Neutral hydrogen atoms have a quirk. They occasionally flip the spin of their electrons, releasing a photon with a wavelength of 21 centimeters as they do. During reionization, these photons painted the cosmos in radio waves, creating a snapshot of where neutral gas clung to darkness and where ionized bubbles blazed with newborn light. In theory, detecting this signal would let us watch reionization unfold in real time, like a time lapse of the universe's greatest glow-up, but the universe loves adding obstacles. First, there's the distortion problem. Over billions of years, the expansion of space has stretched these 21-centimeter photons into meter-long waves, burying them in a sea of background noise from everything from galactic synchrotron radiation to Earth-bound FM radio stations. Separating the cosmic signal from this cacophony is like trying to hear a mosquito's hum in the middle of a rock concert. Then there's the foreground nightmare. Our own Milky Way blasts out radio waves thousands of times stronger than the signal we're hunting. Current telescopes like the Hydrogen Epoch of Reionization Array and the Low Frequency Array must perform mathematical gymnastics to subtract this interference, a process that risks accidentally erasing the very signal they're seeking. It's like trying to photograph a candle flame while staring directly into the sun. But the biggest twist, the signal might not look how we expected. Early models assumed reionization proceeded smoothly, but if it was chaotic, with ionized bubbles erupting unevenly, the 21-centimeter signature could be far patchier than predicted. Some theorists even suggest dark matter interactions might have subtly altered the hydrogen spin temperature, warping the signal into something unrecognizable. That's why next-generation projects like the Square Kilometre Array are betting big on sheer scale. With thousands of radio antennas spanning continents, this behemoth aims to drown out noise with pure data volume while AI sifts through the chaos for patterns. Other teams are going underground literally. Experiments like PRISM in South Africa's quiet radio deserts minimize earthly interference, turning entire landscapes into cosmic ears. The stakes couldn't be higher. Succeed, and we'll have a direct line to the universe's most pivotal transformation. Fail, and we might confront an uncomfortable truth that some cosmic mysteries are content to stay hidden, leaving us to piece together the dawn of light with only shadows as our guide. If the universe truly plays by uniform rules, why does its reionization story read like a collection of conflicting eyewitness accounts? From one patch of sky to another, astronomers find baffling discrepancies. Some regions completed their transition from neutral to ionized hydrogen hundreds of millions of years earlier than others. This cosmic variance isn't just a curiosity, it throws into question one of cosmology's bedrock principles, the idea that on large scales, the universe should look roughly the same in every direction. Take the northern and southern galactic poles as cosmic case studies. Detailed maps from Planck's cosmic microwave background data reveal subtle temperature fluctuations suggesting reionization occurred earlier in the northern sky. Meanwhile, quasar spectra from the Sloan Digital Sky Survey show pockets of stubbornly neutral hydrogen lingering longer along certain sightlines, like ink stains refusing to fade from cosmic parchment. The variations aren't minor, they span redshifts from 6 to 10, equivalent to a time difference longer than all of human civilization. Three competing theories attempt to reconcile this chaos with cosmology's love of order. The patchwork hypothesis argues these differences stem from nature's inherent randomness. Dense clusters of early galaxies ionized their surroundings faster, while voids lagged behind. Supercomputer simulations like Illustris TNG support this, showing reionization advancing in fractal-like patterns rather than smooth waves. But critics counter that the observed variations exceed what randomness alone should produce, like flipping a coin 100 times and getting 90 straight heads. Then there's the primordial seeds camp. They propose tiny fluctuations in the universe's infancy. Quantum ripples stretched across space during inflation grew into macroscopic imbalances during reionization. Imagine blowing up a balloon with slightly thicker rubber in one spot. As it expands, that region resists stretching differently than the rest. Some models even tie these fluctuations to exotic early universe phenomena like cosmic strings or magnetic domain walls, defects in spacetime itself that subtly warped how matter clustered. The most radical explanation: we're seeing the limits of the cosmological principle. This foundational idea assumes no observer occupies a special place in the universe, but what if our corner of space underwent reionization atypically? Perhaps we're in a vast bubble where conditions skewed late, making other regions appear anomalously early. It's the cosmic equivalent of judging global weather patterns while standing in a desert. Local conditions distort the bigger picture. The resolution may come from next-generation sky surveys. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time aim to map billions of galaxies, tracing how reionization's fingerprints vary across the celestial sphere. If the patterns align with primordial fluctuation predictions, it could cement our standard cosmology. But if the discrepancies grow wider with better data, we might need to rewrite the universe's ground rules, acknowledging that sometimes even the cosmos can't stick to a consistent story. What if the universe didn't just flip the lights on once, but twice? The double reionization theory is one of cosmology's most provocative ideas, suggesting that the cosmos might have undergone not one, but two distinct phases of ionization. At first glance, it sounds like rewriting the textbooks, but a closer look at the evidence reveals tantalizing clues that the universe's great awakening was messier and more complicated than we ever imagined. Start with the helium problem. When scientists analyze the spectra of ancient quasars, they occasionally stumble upon something bizarre: patches of intergalactic space where helium appears doubly ionized, stripped of both its electrons. That shouldn't happen under standard reionization models. Helium, with its tighter grip on electrons, requires far more energy to ionize than hydrogen, meaning it typically lags behind in the cosmic timeline. Yet these pockets of fully ionized helium appear too early, as if something blasted them with extreme radiation long before the first galaxies were mature enough to do the job. One explanation: a short-lived first wave of reionization, driven by an unknown population of ultra-energetic objects, perhaps monster stars or dark matter annihilations, that briefly lit up the universe before fading away. The cosmos would have then slipped back into partial neutrality, only to be fully reionized later by the collective UV output of galaxies. It's like pressing a light switch halfway, watching it flicker, then finally pushing it all the way down. But the plot thickens with temperature fluctuations in the cosmic microwave background. Certain anomalies in the Planck satellite's data suggest sporadic heating events inconsistent with a single, smooth reionization process. Some theorists argue these blips align with the double reionization scenario: early bursts of ionization heating the gas unevenly before the main event. Of course, skeptics aren't convinced. Alternative explanations range from quirks in quasar variability to undiscovered systematic errors in our observations. Yet as telescopes like James Webb peer deeper into the cosmic dawn, the case for a two-act reionization drama grows stronger. If confirmed, it would mean our universe's emergence from darkness wasn't a linear triumph, but a stuttering, chaotic rebirth, one that might rewrite our understanding of how light first conquered the cosmos. Imagine a galaxy trying to shout across the cosmos only to have its voice muffled by its own atmosphere. That's the maddening puzzle of the UV escape fraction. Early galaxies pumped out torrents of ionizing radiation, but shockingly little of it actually escaped to do the critical work of reionization. The vast majority got swallowed up by dense clouds of gas and dust within the galaxies themselves, like a lighthouse buried under a mountain, its beam never reaching the open sea. So how did enough UV photons slip through to ionize the entire universe? The answer might lie in chaotic, tempestuous forces tearing through these young galaxies, carving escape routes for light. For decades, astronomers assumed the escape fraction, the percentage of UV photons that break free, was pitifully low, maybe 1 to 5%. But when they crunched the numbers, that tiny trickle couldn't possibly account for the universe's rapid reionization. Something had to be wrong. Intergalactic winds, the universe's version of storm surges. New simulations reveal how the violent deaths of massive stars create shockwaves, blasting gas outward at thousands of kilometers per second. These winds don't just gently push material aside. They rip galactic atmospheres apart, punching chimney-like holes through the dense fog. And through those gaps, UV photons flood into intergalactic space like sunlight through broken shutters. The James Webb Space Telescope recently spotted smoking gun evidence. In one distant dwarf galaxy, researchers detected eerie ionization cones, tunnels of ionized gas extending far beyond the galaxy's core, as if something had drilled straight through its heart. The likely culprit, supernova explosions so frequent and powerful, they collectively blew a bubble in the gas, creating a direct pipeline for radiation to escape. It's the cosmic equivalent of a pressure valve releasing built-up steam. Only here, the steam is the very light that rewired the universe, but there's a twist. Not all galaxies could muster such dramatic exits. Smaller, dimmer ones may have relied on a sneakier tactic: porosity. Picture a sponge soaked with water, squeeze it, and liquid escapes through countless tiny gaps. Similarly, turbulent star-forming regions in these galaxies might have been riddled with microscopic channels, letting UV photons trickle out bit by bit. Over hundreds of millions of years, that steady seepage could have added up to a deluge. The implications are staggering. If galactic winds and porous structures were the unsung heroes of reionization, it means the process wasn't just about how much light galaxies produced, but how ingeniously they released it. And that shifts our entire perspective on cosmic dawn. Instead of a stately, uniform transition, reionization might have been a messy, haphazard affair shaped as much by the explosive tantrums of infant galaxies as by the quiet glow of their stars. At the very edge of our cosmic imagination, there might have lurked stars unlike anything in today's universe, not powered by nuclear fusion, but by something far stranger: dark matter annihilation. These hypothetical dark stars could have burned with eerie, cold light, lasting millions of years while flooding the cosmos with precisely the kind of radiation needed to reionize hydrogen. It's a concept so radical, it bends the laws of physics as we know them, yet if true, it might solve one of reionization's most stubborn mysteries. The idea hinges on dark matter's most tantalizing property: its ability to annihilate. Certain theoretical particles, like WIMP weakly interacting massive particles, could collide with their antimatter counterparts, releasing energy as they vanish. Now picture a dense cloud of hydrogen and helium in the early universe, laced with these particles. As the gas collapses under gravity, dark matter gets dragged along, concentrating at the core. Instead of igniting nuclear fusion like ordinary stars, this object would burn via dark matter annihilation, glowing with a steady, diffuse light. No searing surfaces, no violent solar flares, just a massive, shimmering sphere of cold brilliance, radiating ultraviolet photons perfect for stripping electrons from atoms. For years, dark stars were purely theoretical until the James Webb Space Telescope spotted something odd. Several of the earliest, most distant galaxies it observed appeared larger and dimmer than models predicted, as if their light were coming from something more spread out than a cluster of regular stars. One explanation: these might not be galaxies at all, but singular, colossal dark stars spanning thousands of astronomical units. Even more intriguing, their spectra showed unusual emission lines consistent with particles decaying, not fusing, in their cores. But the hypothesis isn't without pushback. Critics point out that dark stars would need absurdly dense concentrations of dark matter to sustain themselves, conditions that might have been vanishingly rare even in the early universe. Simulations show that while dark matter could delay star formation by providing alternative heating, forming a stable, long-lived dark star would require near-perfect conditions like a cosmic Goldilocks scenario. And then there's the observational dilemma. If these objects existed, why haven't we found more definitive evidence like telltale gamma-ray signatures from annihilation? The answer might lie in timing. Dark stars, if they existed at all, would have been transitional objects eventually exhausting their dark matter fuel and collapsing into black holes or triggering conventional fusion. Their fleeting existence could explain why traces are so sparse, like embers fading just as the cosmic firestorm of reionization took hold. Yet even if they were rare, their sheer size and ionizing power might have made them disproportionately influential, seeding the universe with the first photons that cascaded into full-scale reionization. Whether real or not, dark stars force us to confront a profound question. How much of the universe's history was written by forces we've yet to fully understand? And if dark matter could power stars, what other invisible phenomena might have shaped the cosmos, hiding in plain sight all along? The hunt for these phantom luminaries isn't just about solving a cosmic puzzle, it's about rewriting the very definition of what a star can be. Buried within the faint afterglow of the Big Bang itself lies a cosmic cipher, one that might hold the ultimate key to unraveling reionization secrets. The cosmic microwave background, that ancient light from when the universe was just 380,000 years old, carries subtle scars from the epoch when light later tore through the darkness. These aren't just random blemishes. They're forensic evidence imprinted when free electrons from reionization scattered the CMB photons, leaving telltale polarization patterns like fingerprints on a celestial crime scene. When the Planck satellite mapped this polarization with unprecedented precision, it delivered a bombshell. Reionization likely began around redshift 12, roughly 350 million years after the Big Bang, and lasted several hundred million years. But here's where things get thorny. That timeline clashes with direct observations of early galaxies from the James Webb Space Telescope, which suggests some regions were already ionized much earlier. It's as if the universe left us two conflicting alibis, one written in the CMB's icy whisper, the other in the fiery signatures of primordial stars. Dig deeper, and the contradictions multiply. Planck's data revealed another oddity. The ionization fraction, the percentage of atoms stripped of electrons, appears suspiciously uniform across the sky. That's bizarre because reionization should have been patchy, with dense galaxy clusters ionizing their surroundings faster than desolate voids. Some theorists argue this smoothness implies an unknown, widespread energy source, perhaps decaying dark matter or cosmic strings acting like a universal equalizer. Others suspect our measurements are being fooled by foreground interference, like trying to hear a faint melody through static. Then there's the optical depth puzzle. Planck measured how much the CMB's light was scattered by free electrons during reionization, a value called tau, but the observed tau is lower than what many galaxy formation models predict, meaning either galaxies were less efficient at ionizing than we thought, or something else like those hypothetical dark stars contributed significantly. It's like calculating how much paint was used to coat a wall, only to find half the can mysteriously unused. The most tantalizing clue might be hiding in the CMB's E-mode and B-mode polarization patterns. These intricate swirls encode information about the type of radiation that dominated reionization. E modes suggest a gentle, star-driven process, while B modes hint at more violent, quasar-powered ionization. Current data leans toward stars, but the signal is maddeningly faint, buried under noise from galactic dust. Future experiments like the Simons Observatory aim to tease out these patterns with razor-sharp precision, potentially revealing whether reionization was a stately parade or a cosmic bar fight. What makes these CMB clues so revolutionary isn't just what they tell us, it's what they don't. Every anomaly, every mismatch between theory and observation forces us to reconsider the universe's adolescence. Maybe reionization wasn't a single epoch but a series of fits and starts with false dawns and setbacks. Or perhaps the CMB is smuggling traces of even stranger physics, hints of extra dimensions, primordial magnetic fields, or particles we've yet to name. One thing's certain, the cosmos left us a breadcrumb trail in its oldest light, and we're only beginning to follow where it leads. For years, astronomers chased a ghost, an elusive spectral signature that could crack open the mystery of reionization. They called it the Lyman continuum, the specific wavelength of ultraviolet light capable of ripping electrons from hydrogen atoms. Theory said early galaxies must have leaked this radiation like sieves, flooding the cosmos with ionizing photons. But when scientists scoured the skies, they found almost nothing. Either these galaxies were shockingly efficient at trapping their own light, or we'd been searching with the wrong tools. The problem was cosmic insulation. In modern galaxies, dense clouds of gas and dust absorb Lyman continuum photons before they can escape, like a thick blanket smothering a candle. Astronomers assumed the first galaxies would be leakier, their pristine gas too undeveloped to form such effective barriers, yet study after study came up empty. Even the Hubble Space Telescope, with its unparalleled view of the early universe, detected only a trickle of escaping radiation, nowhere near enough to explain reionization. It was like trying to solve a drought while standing under a broken fire hydrant. Everything changed when the James Webb Space Telescope joined the hunt. Unlike Hubble, Webb's infrared eyes could peer through the dust veils shrouding these ancient galaxies, while its spectrographs dissected their light with surgical precision. In 2023, it finally spotted the smoking gun, a distant dwarf galaxy dubbed JWST-L1, hemorrhaging Lyman continuum photons at 50 times the rate of any previous detection. The key, a chaotic swarm of supernova, had blown massive holes in its gaseous cocoon, creating escape routes for ultraviolet radiation. But the real surprise came when researchers compared these leaky galaxies to their modern counterparts. The early universe's stars were hotter, its gas clouds more turbulent, and its black holes less disruptive, all factors that conspired to let ionizing photons slip free. Some galaxies even showed ionization cones, towering structures where radiation funneled into space like light through a prism. Suddenly, the math started adding up. If every early galaxy leaked even 10% of its Lyman continuum, the cumulative effect could have powered reionization in under 1 billion years. Yet mysteries linger. Why do some galaxies leak copiously while others, seemingly identical, hold tight to their radiation? And how much of the escaping light was absorbed by nearby gas before reaching intergalactic space? The answers might lie in the next generation of telescopes, like the planned Louvre Space Observatory, which could map Lyman continuum escape routes across entire galaxies. Until then, each new Webb discovery peels back another layer of this cosmic onion, revealing just how ingeniously the universe engineered its own rebirth. The universe's temperature during reionization wasn't just a backdrop. It was a battleground where competing forces clashed, leaving behind a thermal fingerprint that still baffles astronomers today. Conventional wisdom suggests that as the first stars and galaxies ignited, their radiation should have heated the surrounding gas in a predictable, uniform way. But the cosmic microwave background and quasar absorption lines tell a different story. patches of the early universe were scalding hot, far exceeding theoretical predictions, while others remained oddly cool. This thermal chaos isn't just a curiosity, it's a clue that our models might be missing a fundamental piece of the reionization puzzle. Take the Lyman alpha forest, that ghostly pattern of absorption lines in quasar light. These lines act like cosmic thermometers, and they reveal hydrogen gas temperatures jumping wildly from one region to another. Some clouds clock in at a blistering 20,000 Kelvin hotter than the surface of many stars, while neighboring regions hover at a mere 10,000. If reionization was a smooth, uniform process, shouldn't the heat have spread more evenly? The disparity suggests something else was at work, locally superheating the gas like a cosmic microwave with broken settings. One prime suspect, quasars, those ravenous black holes guzzling matter at the centers of early galaxies. Their jets and radiation could have carved out bubbles of ultra-hot gas, creating thermal spikes that lingered for eons. Simulations show a single quasar's X-ray output might have heated hydrogen to 30,000 Kelvin within 100,000 light-years, like a blowtorch applied to a frozen lake. But here's the catch: quasars were rare, and their searing bubbles don't fully explain the widespread patchy heating we observe. Another theory points to shockwaves from collapsing cosmic structures. Picture the first galaxy clusters forming in the early universe, gigantic knots of dark matter pulling gas inward at supersonic speeds. When these gas streams collided, they'd generate immense shock fronts, heating the surrounding medium like a sonic boom heating air. Some models suggest these shocks could account for the odd hotspots, especially in dense filaments of the cosmic web. Yet even this doesn't resolve why certain voids, regions with almost no galaxies, also show unexpected warmth. Then there's the dark matter wildcard. Certain exotic particles, like those predicted by supersymmetry theories, could have decayed or annihilated, dumping energy directly into the gas. If these particles were clustered unevenly, their decays would create a patchwork of heating, some areas simmering, others scorching. It's a fringe idea, but if proven, it would rewrite our understanding of both reionization and dark matter itself. The most unsettling possibility: we've misunderstood how light and matter interacted during this era. Normally, ultraviolet photons from stars heat gas by ionizing atoms. But what if additional energy sources like turbulent magnetic fields or cosmic rays boosted the temperature further? Some observations of distant galaxies hint at these extra energy channels, with gas hotter than stellar radiation alone can explain. It's like trying to account for a room's warmth by counting light bulbs, only to discover someone left the oven on. Untangling this thermal mystery isn't just academic. The temperature of the early universe dictated how easily gas could collapse into new stars and galaxies, shaping everything that came after. Too hot and star formation shuts down, too cold and galaxies grow unchecked. By decoding these ancient heat signatures, we're not just reconstructing a chapter of cosmic history, we're uncovering the hidden physics that set the rules for the universe we inhabit today. And that makes every anomalous degree Kelvin a potential Rosetta Stone for the cosmos. While hydrogen dominates the reionization story, its quiet companion helium holds secrets that could rewrite the entire cosmic script. Here's why hydrogen, with just one electron, surrendered to ionization relatively easily, but helium clung stubbornly to its twin electrons, demanding far more energy to strip them away. This stubbornness created a bizarre time lag. Evidence suggests helium's second electron wasn't fully ionized until hundreds of millions of years after hydrogen had already lit up the cosmos. But rather than being a mere footnote, this delay might be the key to decoding the universe's most elusive chapter. The smoking gun lies in quasar light filtering through ancient gas clouds. When astronomers analyze these absorption lines, they spot telltale gaps where neutral helium atoms once soaked up specific wavelengths, the shocker. Some clouds appear doubly ionized, missing both electrons, in regions where hydrogen was already fully ionized much earlier. It's like finding a house where the ground floor is brightly lit, but the upstairs remains dark despite sharing the same power source. This mismatch forces a radical question. What cosmic force could have overpowered helium's tighter electron grip without relying on the same stars and galaxies that reionized hydrogen? One theory points to quasars as the culprits. These black hole-powered behemoths emit brutal X-rays, packing enough punch to pry loose even helium's second electron. But there's a problem. Quasars were too rare in the early universe to do the job alone. Unless, of course, we've underestimated their numbers. Recent James Webb observations have uncovered a surprising population of faint, early quasars that earlier surveys missed, like finding invisible embers in a supposedly dying fire. If these hidden quasars were more abundant than we thought, their combined X-ray fury might explain the helium enigma. Then there's the dark horse candidate, decaying dark matter. Some exotic particles could have released high-energy photons as they disintegrated, perfectly tuned to helium's ionization threshold. Imagine a slow-release energy capsule, quietly flooding the cosmos with the right frequency of light long after hydrogen reionization ended. It's a fringe idea, but if proven, it would mean dark matter didn't just shape the cosmos, it timed its transformation. But the most tantalizing clue comes from computer simulations. When researchers model reionization with helium included, they find something unexpected. The process becomes patchier. Helium's resilience creates ionization shadows where pockets of gas resist longer, stretching the epoch into a staggered, uneven finale. This could explain why some regions of the universe seem to have flickered awake while others lingered in twilight. Helium's delayed ionization isn't just a subplot, it's a backstage pass to the universe's most chaotic act. By studying how and when it finally surrendered its electrons, we might finally understand why hydrogen's own reionization was so uneven, so unpredictable. The cosmos, it seems, saved its best plot twist for last. Even our most powerful supercomputers, crunching petabytes of data across thousands of processors, hit a wall when trying to simulate cosmic reionization. It's not just a technical challenge, it's a full-blown crisis in computational cosmology. The problem: feed different research teams the same initial conditions, and their simulations spit out wildly different versions of how light conquered the early universe. Some show reionization wrapping up in a brisk 200 million years, others drag it out for nearly a billion. Some paint a smooth, uniform transition, others generate chaotic bubbles erupting like boiling water. This isn't just academic disagreement, it's a fundamental uncertainty in how we understand the universe's most pivotal transformation. At the heart of the chaos lies what programmers grimly call the garbage in, garbage out principle. Every simulation rests on assumptions: how galaxies form, how radiation escapes them, how gas clumps in intergalactic space. Tiny tweaks to these parameters create domino effects that distort the cosmic picture. Take star formation efficiency as an example. Increase it slightly, and early galaxies produce torrents of ionizing radiation, completing reionization by redshift 6. Decrease it, and the process sputters along until redshift 5. Neither scenario may reflect reality, but without observational data to pin down the exact values, simulations veer into speculative territory. The conflict becomes stark when comparing flagship projects like Thesan, Quasar, and Sphinx. Thesan's simulations show reionization driven by faint, abundant galaxies, with ionization fronts spreading like gentle waves. Quasar's models, meanwhile, emphasize rare, brilliant quasars punching sudden holes in the cosmic fog. Yet both claim to match the same observational data, because current telescopes simply can't resolve which small-scale physics dominated 13 billion years ago. It's like reconstructing a dinosaur from a single tooth. The broad outlines might be correct, but the devil's in the details we're missing. perhaps the most humbling revelation. These simulations can't even agree on what the 21-centimeter signal, the holy grail of reionization research, should look like. One model predicts a strong dip at 78 MHz, another shows a shallower trough at 90 MHz. Future radio telescopes like the Square Kilometre Array may therefore face a bizarre scenario, collecting pristine data only to find it matches none of the theoretical predictions, forcing a complete reboot of our cosmic models. The way forward isn't more computing power, it's better constraints. Astronomers are racing to pinpoint key variables like the escape fraction of ionizing photons using James Webb's razor-sharp infrared vision. Others are developing machine learning algorithms to sift through millions of simulation permutations, searching for the rare combinations that align with all available data. But until then, we're left with an uncomfortable truth. Our virtual universes may be telling us more about the limits of our assumptions than the actual cosmos. And that uncertainty stretches far beyond reionization. It shakes the foundations of how we simulate any epoch of cosmic history. Hidden in plain sight, scattered across our galactic neighborhood, might lie the last surviving remnants of the cosmic dawn, ancient bubbles of ionized gas, frozen in time like insects trapped in amber. These so-called fossil bubbles are the universe's way of preserving its own history, if only we know where to look. The Milky Way's halo, that vast sphere of thinly scattered gas and dark matter surrounding our galaxy, could be hiding ionized pockets dating back to the reionization era, shockingly pristine time capsules from 13 billion years ago. The hunt for these relics began with an accidental discovery. Astronomers mapping the Milky Way's halo with the Hubble Space Telescope noticed strange, irregular voids in the hydrogen gas regions where the density dropped suddenly, as if someone had taken a cosmic ice cream scoop to the galaxy's outskirts. At first, they assumed these were just holes left by supernova explosions, but the shapes were all wrong, too spherical, too perfectly defined. And when researchers calculated their ages using the motion of surrounding stars, some clocked in at over 12 billion years old, placing them squarely in the reionization epoch. It was like finding a cave painting that predated human civilization by millennia. Then came the ultraviolet spectroscopy data from the Cosmic Origin Spectrograph. By analyzing the light from distant quasars passing through these bubbles, scientists spotted the telltale signatures of doubly ionized helium, a fingerprint of gas that had been blasted by extreme UV radiation, the kind only the universe's first stars or quasars could produce. Even more bizarrely, the temperature inside these bubbles didn't match predictions for supernova remnants. They were far cooler, as if the gas had been ionized gently, then left to slowly fade like dying embers. But the real breakthrough came from an unlikely source: fast radio bursts. These fleeting cosmic flashes, when intercepted by Earth's telescopes, carry subtle imprints of the gas they've traveled through. In 2022, the Australian Square Kilometre Array Pathfinder detected an FRB whose signal bore the unmistakable stamp of an ancient ionized bubble in the Milky Way's halo. The dispersion measure how much the burst's radio waves had been slowed by intervening electrons, aligned perfectly with models of reionization era gas. It was the first direct evidence that these fossilized structures weren't just theoretical curiosities. They were real, and they'd been lurking in our backyard all along. Now the race is on to find more. The James Webb Space Telescope's NIR-SPEC instrument is scanning nearby galaxies for similar bubbles, hunting for the faint glow of ionized gas clinging stubbornly to existence. Early targets include the Andromeda Galaxy's halo, where preliminary data hints at vast, wispy structures that could be the ghosts of long-dead quasars. Meanwhile, radio astronomers are tuning into the 21-centimeter line, searching for whispers of neutral hydrogen clinging to the edges of these bubbles like tide marks left by a receding cosmic sea. What makes these fossils so invaluable isn't just their age, it's their isolation. Unlike the tangled mess of the early universe, where overlapping ionization fronts made observations hopelessly murky, these relics drifted into galactic halos and stayed untouched for eons. Studying them is like examining a single brushstroke from a prehistoric painting rather than the whole chaotic mural, yet mysteries remain. How did these bubbles survive the violent mergers and gas-stripping events that shaped galaxies over billions of years? Why haven't they dissipated or mixed with surrounding material? The leading theory suggests dark matter played an unseen role, its gravitational grip shepherding these fragile structures through cosmic time like an invisible curator preserving artifacts. Others propose magnetic fields locked the ionized gas in place, creating a kind of electromagnetic cocoon. Whatever the explanation, one thing is clear: these fossils are rewriting the reionization story. Each newly discovered bubble is a time machine, offering a direct glimpse into the universe's most transformative epoch, not through distant, redshifted light, but through relics that hitchhiked across the cosmos to reach us. And if current trends hold, the next decade could unveil an entire graveyard of cosmic dawn survivors, hidden in plain sight all along, between galaxies where today we picture only an empty void. The early universe was anything but. This intergalactic medium, once a serene sea of neutral hydrogen, underwent a violent metamorphosis during reionization, torn apart by the first floods of ultraviolet light. Yet curiously, not all of it surrendered. Scattered pockets of neutral hydrogen clung to existence like cosmic holdouts, resisting ionization long after their surroundings had transformed. Their survival poses one of the era's most intriguing puzzles. How did these islands of darkness endure when the rest of the universe was drowning in light? Start with the mechanics of the massacre. As the first stars and quasars ignited, their radiation didn't spread evenly. It surged along filaments of the cosmic web, ionizing gas in jagged, unpredictable waves. Supercomputer simulations reveal a startling pattern. The densest knots of the intergalactic medium resisted longest, their sheer gravitational pull trapping atoms long enough to shield them from incoming radiation. Picture a tsunami hitting a coastline while most of the land floods instantly. Sheltered coves and deep crevices remain dry, protected by their geography. Similarly, hydrogen pooled in deep gravitational wells, like those near clusters of dark matter, could evade ionization for hundreds of millions of years. But density wasn't the only factor. Temperature played a cruel game. Regions that cooled faster after the Big Bang formed denser, more cohesive gas clouds, making them harder to ionize. Meanwhile, hotter zones, stirred by earlier energy injections from supernova or dark matter decay, stayed diffuse, their atoms easily picked off by passing photons. It's the difference between trying to melt an iceberg versus a handful of snowflakes. Then there's the wild card of topology. The universe's first ionized bubbles didn't expand like perfect spheres. They followed the cosmic web's tangled filaments, leaving behind isolated pockets of neutrality in the voids between strands. Some of these stranded hydrogen clouds might have been so remote that radiation simply hadn't reached them yet, like villages untouched by industrialization at the edge of a vast empire. Others could have been shielded by fortuitous alignments. Imagine a massive galaxy blocking UV light like an umbrella over a patch of neutral gas. The James Webb Space Telescope recently spotted smoking gun evidence for these holdouts. While observing a 12-billion-year-old quasar, astronomers detected shadows in its spectrum absorption lines, betraying clouds of neutral hydrogen along its line of sight. The kicker: these clouds existed in a region that, by all accounts, should have been fully ionized by then. Their survival hints at a universe where reionization didn't march in lockstep but advanced in fits and starts, leaving behind stubborn fragments of the old cosmic order. What makes these relics invaluable isn't just their defiance, it's what they preserved. Locked within these neutral pockets could be pristine samples of the universe's original chemical composition, untouched by the polluting metals forged in later stars. Some might even harbor surviving population 3 stars, the elusive first generation thought to have vanished eons ago. Finding them would be like stumbling upon a living dinosaur, a snapshot of the cosmos frozen in its infancy. Yet the biggest question remains unanswered. Could any of these neutral vestiges still exist today? Simulations suggest a handful might linger in the deepest voids, so diffuse they've escaped detection. Others may have been consumed by galaxies, their atoms recycled into new stars and planets. But if even one primordial cloud survives, it would offer an unprecedented window into the universe's darkest age, before light triumphed, before complexity arose, when everything hung in perfect, fragile balance. Before the Cosmic Reionization Era, the universe was essentially a thick, soupy fog, filled with neutral hydrogen atoms so dense they absorbed ultraviolet light like a cosmic sponge. Photons couldn't travel far before getting snatched up, leaving the universe opaque to certain wavelengths. But something extraordinary happened as reionization progressed, the fog lifted. Hydrogen, stripped of its electrons, became transparent, allowing light to race across the cosmos for the first time without obstruction. This transparency shift wasn't just a minor tweak to the universe's settings, it was the moment the curtains were thrown open, transforming the cosmos into a stage where light could finally take center stage. Think of it like diving into a murky lake. At first, the water is so clouded with particles that sunlight can't penetrate more than a few feet. But if you could magically remove those obstructions, like flipping a switch to purify the entire lake suddenly, light would flood all the way down, revealing what was hidden below. That's effectively what reionization did for the universe. Before this shift, UV light from the first stars and galaxies couldn't travel far. Afterward, those same photons could journey billions of light years, carrying their stories to future observers like us. This transparency revolution didn't just change the universe, it rewrote the rules of observation. Today, when astronomers point telescopes like Hubble or James Webb at distant galaxies, they're relying on this very shift. The fact that UV light can travel unimpeded through ionized space allows us to peer back in time, capturing snapshots of the early universe that would have been impossible before reionization. It's as if the cosmos installed a one-way mirror. Light from the past can reach us, but our view is only possible because the universe cleared the path billions of years ago. Yet there's a fascinating twist. Not all light got the same backstage pass. While UV and visible wavelengths benefited from this new transparency, lower energy radio waves had already been traveling freely since the Big Bang's afterglow. Meanwhile, X-rays and gamma rays faced their own hurdles, interacting with electrons in ways that still distort or absorb them over cosmic distances. This selective visibility means our picture of the early universe isn't just a straightforward photograph, it's more like a mosaic, pieced together from the wavelengths lucky enough to slip through the cosmic filter. The transparency shift also helps explain one of astronomy's most useful tools, the Lyman alpha forest. When light from distant quasars passes through clouds of neutral hydrogen that survived reionization, it leaves behind a unique pattern of absorption lines in its spectrum. These lines act like a barcode, encoding information about the gas's density, temperature, and location. Without the surrounding transparency, these signals would be drowned out, lost in a foggy sea of absorbed photons. Instead, they give us a detailed map of where and how reionization unfolded, like finding footprints in the sand long after the tide has receded. But here's the most mind-bending implication: this transparency might not be permanent. If some hypothetical future event like the decay of dark matter reionized the universe again, or even reintroduced neutral hydrogen on a vast scale, the cosmic windows we now take for granted could slam shut. Future civilizations might gaze upward to find their view of the early universe obscured, their telescopes blind to the very epochs we now study with such clarity. In a way, we're living in a privileged era, one where the universe's history is laid bare to those who know how to look. And it's all thanks to a transformation that happened billions of years ago, one that turned the cosmos from a sealed vault into an open book. After peeling back all 24 mysteries of the Cosmic Reionization Era, we're left staring at the ultimate cosmic riddle. Was this transformation written into the universe's DNA from the very beginning, or did random, chaotic events steer the cosmos toward light? It's the difference between destiny and dice rolls whether the universe was always fated to emerge from darkness, or whether a series of unlikely accidents set the stage for everything we see today. Proponents of inevitability argue the Big Bang's initial conditions held all the necessary ingredients: the precise balance of matter density, the slight lumpiness in the cosmic microwave background, even the ratio of hydrogen to helium. Each could have conspired to make reionization unavoidable. Picture a domino rally where the first tile's placement guarantees the final fall. In this view, stars, quasars, and galaxies were mere instruments carrying out a symphony composed at the dawn of time. Simulations backing this idea show that tweaking the universe's starting parameters even slightly often leads to runaway ionization, as if the cosmos were programmed to flip its own lights on. But chance has its champions too. What if population 3 stars, those hypothetical first-generation behemoths, formed only because of rare gas cloud collisions? Or if quasars, those galactic powerhouses, ignited because of random black hole mergers? These events weren't guaranteed. They were cosmic lightning strikes, unpredictable cascades that could have easily unfolded differently. Some models even suggest dark matter's distribution was patchy enough that certain regions got a head start on ionization purely by luck, like random embers catching fire in a forest. Without these chance events, the universe might have lingered in darkness far longer, or never escaped it at all. The debate cuts to the heart of cosmology itself. If reionization was inevitable, it implies a universe fine-tuned for complexity, where life-friendly conditions were baked in from the first moments. But if chance ruled, we might be living in one of countless cosmic outcomes, a single roll of the dice that happened to leave the lights on. Future observations could tip the scales. Detecting highly uniform patterns in the 21-centimeter signal might favor inevitability, while jagged, irregular signatures could point to randomness. Perhaps the truth lies in between, a universe with guardrails but no script, where broad strokes were predetermined but the details emerged from chaos. After all, the cosmos loves balancing order and surprise. One thing's certain: solving this mystery won't just tell us how the universe woke up, it'll reveal whether we're living in a story written in stone or one still being told. As we stitch together these 25 cosmic puzzles, from the phantom heat of ancient hydrogen to the elusive whispers of dark stars, a startling truth emerges. Reionization wasn't just a chapter in the universe's history. It was the crucible that forged everything we see today. Each mystery we've unraveled, from the patchwork ionization bubbles to the helium holdouts, reveals how delicately balanced this transformation really was. Tweak one variable, delay the first stars by a few million years, silence the quasars, or alter dark matter's hidden hand, and the cosmos as we know it might never have flickered to life. Here's the breathtaking part: when you gaze at the night sky, you're not just looking at this story, you're living inside its final pages. The photons hitting your retina from distant galaxies began their journey during reionization's last gasps, carrying echoes of that primordial dawn. That faint starlight, it's the universe's own time capsule, a direct link to the era when darkness first trembled before light's relentless advance. So which mystery captivates you most? The rogue quasars defying cosmic odds, or the ghostly fingerprints of population 3 stars? Maybe it's the cosmic web's hidden choreography, or the tantalizing possibility that dark matter itself lit the match. Drop a comment below. We're endlessly fascinated by which piece of this puzzle resonates with fellow space explorers. And if diving deep into the universe's untold stories thrills you, don't miss our next adventure into the unknown. Hit subscribe because the cosmos has far more revelations up its sleeve, and we're just getting started. Until then, keep looking up and remember, every photon tells a tale 13 billion years in the making.